7 valence electrons. Okay. And we also looked at the similarities in terms of their stabilizations. Carbocations and radicals follow similar kind of stabilities. Benzylic carbocations, allylic carbocations are the most stable because of resonance. Similarly, benzylic radicals and allylic radicals are also very stable because of resonance. Now, I want you to remember the difference between rearrangement and resonance. Resonance is just movement of electrons within the structure, whereas rearrangement can include the movement of an atom within the same structure. Okay? And whenever we are drawing our hooks, just split the bond evenly, and then the radical will go towards. So this is a splitting or causing unpairing, and this step is causing the pairing of the electrons. And we looked at the weakest sites of how the radicals will form, where the radicals will form. Radicals will form in such a manner that the most stable radical forms. So within the structure, you have to locate that hydrogen where abstraction of which will give you the most stable radical. Whenever you will get a allylic radical, you have to show, you have to know both the resonating forms of that radical. Whenever you will get allylic radicals or benzylic radicals. The important part of this chapter is this halogenation reaction. Whenever you will have an alkane, the only way to functionalize an alkane is by having halogenations, free radical halogenations. You need to know these steps. Your halogens may change, your alkanes may change, but the overall general steps will not change. Remember what is initiation? You have a neutral molecule, it splits evenly, and you get your two radicals. This is your initiation step for halogenation. The next is abstraction of the hydrogen by this bromine. So there are only these two propagation steps that are possible in your halogenation reaction, nothing else. So the halide radical will grab the hydrogen, and the alkyl radical will grab the halogen. So opposites are happening here, but overall you start with one radical, you end up with the other radical. You start with one radical, you end up with the other radical. So know your mechanism for this particular reaction very well. So this is the first mechanism that we have looked at for radical mechanism, the free radical mechanism. Okay, and so we also looked at how allylic brominations are being done. Instead of using this setup where electrophilic aromatic reactions can occur, we are now going to use NBS, the N-bromosuccinamide, in presence of a peroxide. What does this NBS do? It releases bromine in smaller concentrations. When the bromide radical is formed in smaller amounts, not in excess, when it is formed in smaller amounts, it will preferably go to the most stable site. So for example, in this particular structure, this hydrogen abstraction creating this particular radical will be the most stable radical that we have seen. Always make sure that your radical, allylic radical, will undergo a resonance. The pi bond splits and this radical goes and forms or couples with this electron right here. So I'm going to draw the main frame exactly like this. So when I am drawing, you should also be drawing on your paper. So you will see better results. So these two form the bond and this electron is left behind. Now this is a secondary allylic radical. This is a tertiary allylic radical. Both of them will get the bromide radical. Where is this bromide radical coming from? It's coming from NBS. NBS and HBr, they will create your bromide radical. So you need to be able to recognize these reaction conditions. Where is this bromine going to go? At this location. Where is this bromine going to go? At this location. Both of these products will be possible by using these reagents for this structure. Any questions so far? So if you look back on A, where will the most stable radical form? Now there are a couple of places where this can happen. If you look at this carbon, this is also allylic, A, B, C, right? So this hydrogen, HA, is an allylic site. But what kind of an allylic site? A primary allylic site. What about this? This carbon is
tertiary.
very good. So this is tertiary, not just tertiary, it is a tertiary allylic. And what about this site? This is also very stable. Very stable. Why? It is a benzylic site. This is also benzylic, tertiary allylic, benzylic. And this is primary allylic, benzylic. Right? What about this one? This is a secondary. This carbon is attached to two other carbons. So it is secondary in position. But this is also secondary benzylic plus it is secondary allylic also. So out of all of these, A, B, and C, because this carbon is more resonance stabilized, there is no doubt this radical will be hyperconjugatedly stable. But the spread of electrons causes more stabilization. Okay, so there is this sigma effect, and then there are this pi effect. This hydrogen right here, this carbon site right here, has both sigma plus pi effects. And so out of all these structures, it is this hydrogen which will be the most stable radical, and hence the chlorine will go attach it later. First of all, the radical will form. So the radical will form here. If there was only one radical to form, this would be the radical to form. Okay. So know which hydrogen will be abstracted out. Always think about which will be the most stable radical that you will get. So for that, you need to have your stability understanding. So after the halogenation of alkanes mechanism, and I hope all of you are clear on that, you will need to know your steps for halogenation reactions, and only bromination and chlorinations will be done. The second mechanism that we are going to look at is the anti-Markovnikov's rule. And if you remember, what does anti-Markovnikov rule do? It is HBr in presence of a peroxide. Usually when you will have HBr, just HBr, it undergoes electrophilic addition in Markovnikov's rule, follows the Markovnikov's rule. What does that mean? It means that the electrophilic part goes to the less substituted carbon and the nucleophilic part goes to the more substituted carbon. This is what Markovnikov's rule tells us. So what would the product look like? It would look something like this. So this is something that we have done in our module 9, right? Any questions on this? So based on the fact that hydrogen will go to the more substituted carbon of the alkene, I want you to remember, what does the electrophilic addition reaction does? What is the first step? You have a pi structure, and that pi structure attacks what? The electron poor or the electron deficient. This is what it does. The pi attacks the electron deficient, electron rich, electron poor, the full curved arrow. Once it abstracts it out, the hydrogen breaks away. So what is the first step happening? The hydrogen is adding across the pi bond. Okay, this is what is happening at the first step. So hydrogen goes where? The hydrogen goes to the less substituted carbon. Why? So that a more substituted carbocation, a more stable carbocation can be generated. Do you all remember this step? Do you have any questions about this step? But in presence of our peroxide, okay, the same structure, and we'll look at it. In presence of peroxide, HBr, HOOH, a radical has to form, but now the bromine adds first. Why? So that a more stable, more substituted radical could form. So out of this less substituted and more substituted site, the bromine, the incoming bromine goes to the less substituted carbon and the radical forms at the more substituted carbon. That is the only difference that happens between the electrophilic addition and this free radical mechanism reaction. Okay. So also remember, why does this happen here? What if the radical had formed here? Please remember, we just looked at it. Carbocations can rearrange. Okay. But radicals cannot rearrange. So they have only one shot at doing what they have, at creating the radical. So they will look out for the most weakest spot. Any questions? Okay, I'll assume there were no questions. So initiation, that is our first step to start the reaction. And so let's do a proper example. For an example, right here. And we are not going to worry about resonance or anything like that. HBr, ROR. R could be any alkyl group. R could be any hydrogen also. So for initiation, what is the first step? Will the HBr break or this oxygen-oxygen bond break? So we will look in our bond dissociation energy, and we find that the bond strength between the oxygen and oxygen is very, very small. And so the first thing that will break is ROOR in presence of light. Because I did not show you light, I'm just going to assume there was light. In presence of light, clean split occurs. So how many molecules of radicals will I form? I have formed 2 radicals. Now, before anything else happens, the RO gets the HBr. So a hydrogen abstraction occurs. ROH plus Br radical. Now you might argue that this is a propagation step. I started out on this side, there was 1 radical, on this side there is 1 radical, okay? But this radical formation is something that forms during the initiation step. So that is one difference that I wanted you to see. If you are asked, always remember, from a neutral molecule, whenever you create a radical, that is definitely your initiation step. But this is bromide radical that forms, not the H radical. There will never be a H radical forming. Okay, the bromide radical forms. The next step is our propagation phase or the propagation steps. This is, you have a pi. Now I want you to remember, when you have HBr with peroxide, you are going to do you are going to do addition across the pi bond. But when you will have NBS, then you will have to add bromine across the allylic side. So know your reagents, recognize your reagents. So this is your alkene and this is your bromide radical. What propagation step are we going to do? If you go back and look in the mechanisms that we have looked at, 11, 9, I think, right here. If you look at our propagation steps, which propagation step are we going to do? We are going to do addition to a pi bond. You have this halogen and you are going to add it on your alkene. This is what we are going to do as well. We have a radical. There is going to be a clean split. I should make the hook at this carbon. So this hook goes to this carbon. This hook goes to this carbon. Okay, ideally, these 2 radicals form. And so this bromide will go where? Will it go to this site or will it go to this site? If it goes to this particular radical site, you will get a secondary radical. But if it goes to this site, oops, you will get this radical. So out of these two, which pathway will happen? The pathway where the more stable radical will form. This pathway will not occur. So the bromide radical is going to go and make this particular new radical. So in the starting materials, you have one radical. In the product side, you have one radical. So the propagation step goes on. So this addition to pi bond. Remember, for the incoming radical, for the formation of this radical, you have to keep in mind the most stable radical that can form. Okay. The next step of our propagation remember this HBr, we are going to use it again. So abstraction of a hydrogen. Unpairing occurs, the hydrogen and the bromide are ready. This radical wants to make a new bond. BrH plus bromide radical. I know it's a little confusing, but just remember, generation of bromide radical is a very important part of your main reaction here. Okay, any questions? Any questions from your propagation steps? So this is hydrogen abstraction propagation step. This is addition to pi bond propagation step. Okay, did I ever make a H radical? Never. Okay, and there will be a variety of termination steps. For termination, all these radicals that you're forming, you will get some byproducts. So this bromide can actually get in touch with this radical also. But these are useless for our synthetic purposes. So we don't have to worry about them. So one of the side or byproducts that will form is this. But you cannot state, if I give you this particular reaction and you give me this product, it will definitely be 0 points. Because this is a side product and that is not your major product. This is what the major product is. Another termination that can happen is you have two bromide radicals and then you get a bromine. Okay, one other that you can get is you have this radical also, these kinds of radicals also. So Br radical with the Or radical. So different permutation combinations can happen for us in these termination steps. So for any benefit of the mechanism, the initiation and the propagation steps, These are the only important mechanistic steps for this particular mechanism. You don't have to worry about the termination steps. I will also not ask you anything about the termination steps of this mechanism, but you must know the mechanism for halogenations of alkanes and the anti-Markovnikov additions of these alkenes. Okay, very quickly, let's check where we are right now. Did I not switch it up? So for the same structure, write it in your notebooks. What will be the product here? And for the same structure here, draw a reasonable structure for this reaction. Same structure, different products. Go ahead, you can look in your notes. Think about it. If you want, you can discuss also with your colleagues or with me if you have a doubt. But if you're confident, then that's great. Anybody wants to help figure out the products? Portia, you want to help me with this particular reaction? Okay, you don't have to be scared or worried. Anybody? We just did this.
Sure. It'll just be the anti-Markovnikov for the first one, so BR will go on the look. So yeah, it'll go 2 over from that methyl group.
So where will it go? On the alkene or away from the alkene? Okay, let me label these A, B, C.
On B.
B, very good. That's right. Thank you, Nelson. And that's what we just did a minute ago. We had the structure and that's where it will go. And do you want to help me with this NBS question also?
Sure. It'll be on A for NBS because it's just Markovnikovs.
So that's what I want all of us to know. Thank you, Nelson. When you have NBS and the peroxide, we are not doing electrophilic addition. It is still the radical mechanism. Okay. And where's my file? So whenever you will have NBS, we will be doing a allylic addition, not a electrophilic addition. And I'm trying to find my own notes where we just looked at it. Apparently, we did not look at it. Oh, right here. So we have this alkene. To avoid adding bromine on the alkene, that's why we use the NBS. When we use the NBS, the concentration of the bromide radical will be very low. Okay, and that's when it will only go to the allylic sites, not on the alkene, but on the allylic site. Okay, so that's what I wanted all of us to see the difference upon. But thank you so much, Nelson, for helping us. So how many allylic sites do I have? I have A, B, C, and then B, and C, and then A, B, and C. All of these three are my allylic sites on this example. So I can get all of these three plus three more. Do you know why? Because every time I will do a allylic product, allylic radical, it is going to shift electrons. So having a bromide here or bromide here, it is exactly same thing. Right? So from this, when the allylic site will change, when the allylic resonance will occur. And let's just say that I had this radical earlier. Now I'm going to split it. This is the radical that is going to form. So we don't say this is a Markovnikov's, but this is still a free radical mechanism where the allylic resonance has occurred. So A product, 1 number, 2 number, and then I have third product from here. From this second structure, what radical will I get? I'm getting a radical right here. So I will do the resonance, splitting occurs, pairing occurs. So this is just a repetition of our resonances also. And so this is also a kind of product that we can get. So 4 different kinds of products. Plus, these are chiral sites. Do you remember what would that do? Chiral sites, if one of them is R, we will also have the S form. If this is R, we will have a S. But in this, both of these, this side and this side are the same groups. So no R and S. This is not a chiral site. This is a chiral site. This is a chiral site. And this is a chiral site. So RS, RS, RS. So 7 total products can be possible from this particular structure. Okay, too much? A lot? Is this a lot? But the good thing is we are almost at the end of our radical mechanisms. Let's very quickly look at other important radical reactions also. And so autooxidations that happen because of the presence of oxygen in human beings or any living being and causes cell damage. And that's why we are encouraged to eat antioxidants, right? So this oxygen, that is the source of our diradicals. Plus ozone layer. When ozone gets depleted from our atmosphere, it causes further damage to our skin, which increases the formation of these radicals from oxygen because sun's rays can now reach the earth more. So how is this ozone depleted? So ozone is depleted by all the chemical sprays that we are using. All the perfumes, all the body sprays, all of those, and all the canola bar sprays. All of them have some form of CFCs, chlorofluorocarbons. Even though there is a reduction in the use of these chlorofluorocarbons in our newer varieties of these sprays, but still it is not enough. So the damage to the ozone layer is done because of these chlorofluorocarbons. And then chlorine radicals form when they are with ozone. From where does it form? The rays of the sun. The heat of the sun forms these chlorine radicals, which interferes with the ozone formation cycle. So this is an important climate impact that the radicals are causing, and important impacts that radicals are forming within our bodies also. There are a few problems that are associated with radical reactions, and that is why we only have one module where the radicals are being taught. The first problem that we face with radicals is that they are chain reactions. They are very hard to control. Once it starts, you don't know what all side products or byproducts will form. Okay? So that is a very, very difficult part to control. So usually for synthetically useful reactions, we do not use radical reactions very easily. Even though the propagation steps are self-sustaining, the radicals once start to form, you don't know when they are going to terminate or when the faster rate will terminate. Again, a problem of not being able to control it. Another problem that we face with radical reactions are polychlorinations. So if you remember, we had looked that bromine is slow and selective. It will only go and form a radical at the weakest carbon, which will generate the most stable radical. On the other hand, chlorine is very fast and non-selective, which makes it replace practically every hydrogen that is there. If you have a bigger structure, you have more hydrogens. All of these hydrogens can be replaced by chlorine. Okay. So that is a huge problem that we face with chlorinations. So these are the three main problems that we face with radicals. Another thing that we look in radicals is the presence of inhibitors and initiators. So we know which are our initiators: light and heat. These are definitely our initiators of radical reactions. But for these to be able to initiate a reaction, we also need to have proper kind of reagents. So this is also a peroxide kind of a reaction structure. I'm sorry. This is an acyl peroxide. 1, 2 carbon, 1, 2 carbon at least. This part can be R, any alkyl, or it could be a hydrogen also. Okay, and it is a very, very small amount of heat or light or energy that you need to split up this oxygen-oxygen bond to form your radicals. Okay, so you will get two molecules, similar molecules, because they are symmetrical molecules. So for our initiators, you also need to have a good starting material. For example, you can have bromine. This can split. You can have peroxide. These can split easily. So these are good starting materials for the light or heat to be able to start our free radical reactions. The initiators, and then there are inhibitors. As the name suggests, they will inhibit formation of more radicals. If you remember, there is an initiation phase, a propagation phase, and then a termination phase. So inhibitors can do two things. They can interfere in the propagation step. Instead of bromide radical and approaching an alkane, which it wants to abstract the hydrogen from, the bromide radical will now have to face another reagent, which is more, which will form more stable radical. So instead of reacting with the alkane, the bromide would start to react with that new material, which is going to form a more stable radical. Did you understand what I just said here? What is the problem with inhibitors in the propagation step? So inhibitors start to compete with your actual starting material. It can also interfere in the termination process. Instead of your bromide reacting with your alkanes radical, this bromide can start to react with that other stable radicals structure. So these can combine instead of these combining together. So this is what it is going to do. It is going to scavenge the free radicals to stop chain reaction processes. Stop chain reaction processes which we desire. Not there will be free radical reactions going on, but not the desired chain reactions. So oxygen molecules in air, from air, and hydroquinone. So usually when a chain reaction is going on, the scientists would just add a little bit of hydroquinone. It would terminate the chain reaction which is going on. So a little bit of it is added deliberately also to stop the chain reactions which are going on. Any questions? You don't have to know any of these structures or the reaction mechanisms here, but you must know how the resonance is happening here. Okay, I will not be asking you any hydroquinone kind of a question, but I can give you the structure and I will ask you what will be the resonance stabilization from here. Because I expect you to know all the propagation steps, all the initiation steps, and the termination steps. So the 6 mechanistic steps that are involved for your radical mechanisms. All right, I guess we've already looked at our other important radical reactions. Now, I was planning to finish up to this part yesterday. So which is the Wednesday, today is Thursday. And I was planning on to do our polymerizations of alkenes from today. However, because of that one day that was out of schedule for us, I'm planning to drop polymerization of alkenes from our course. Okay, I hope it's not going to make any one of you sad if you were looking up for the time when the polymers will be stated. But if you're interested, we also offer a polymerization course, but it's a 4,000 level course that is offered at Xavier. However, I will not be doing polymerization reactions in here for our course. So if you see any old questions or if you see all of this material in these slides, you can ignore them. You don't have to prepare them for your final exam preparations. Any questions? Okay, but we will be looking at these slides, the 1138. So on 1138, I have a resonance stabilization. that I wanted all of you to see. So there is this radical in the benzylic site and how the radical moves throughout, how the double bond breaks, how the radical pairs with this other electron. So that's what I wanted all of you to see here. Now looking at the synthetic importance, you have an alkane. You can make an alkene starting from this alkane. Now remember, there is nothing, practically nothing, no functional group, no anything on this structure. And so how are you going to make alkene from this alkane? So to do this, you need to functionalize your alkane. How do we do that? There is only one method by which you can functionalize your alkane. The only method is by halogenation. Now pay attention to this reagent. The reagent that I used is NBS. What does NBS do? It gives you bromine radical in low concentrations. When you have a low concentration of the radical, it will only form the most stable radical. And out of all the potential sites here, where is the most stable radical, where it can form? Not at any secondary location, not at any primary location, but at this tertiary location. And that's where your bromide radical will go and get attached to. Any question on why this bromide forms? So now since this bromide has formed, you can make this alkene. How can you make this alkene? So think about it. Number of carbons are exactly the same. The functional group transformation, you know what is. You have a leaving group and you have an alkene. So what is the reagent that you're going to use? Before you do that, look in the product. Is there any rearrangement? Do you need a protic solvent? Do you need a protic condition which will cause the rearrangement? What is the stereochemistry of your groups? Fortunately, there are no stereochemical problems here, but we do have a regiochemical problem. What is the position of the alkene? Is it Hoffman or is it Zetsavs? The more substituted alkene, the less substituted alkene. Based on that, you will use your reagent. If you use sodium ethoxide or sodium amide, either of these two, which are regular bases, not bulky bases, you are going to get your Zetsavs product. However, if you need a Hoffman product, then what kind of a base would you use? You need to use a bulky base, the potassium terbiroxide, which will give you the Hoffman product. So depending on which alkene you have to create, that's what you will use. You need to know your bases at that point. Okay, I'm not going to discuss this synthesis problem. This is the product right here. And we looked at a structure like this 2 days ago. You have to start from this material and end up at this material. So how many carbons do you have in your starting material? 3. Number of carbons has changed. Since you have increased the number of carbons, you know that you are going to add an acetylide. The acetylide has to be added on a primary substrate. Don't forget that. So when you're increasing in the number of carbons, just remember that your acetylide will add to a primary or a methyl kind of a substrate. Any questions so far? All of you are understanding what's going on? Any questions? So because you have this, you don't have anything, no functional group on it. You are going to do your free radical reactions. Where the bromine will go? 1, 2, 3 to the second carbon. Why? Because that is the secondary location. This is a primary location, primary location. So your bromide is going to go to the secondary location. At this point, you want to create a alkene. If you remember your alkynes, this is one of the methods by which we create alkynes. How is that going to happen? When you will have this alkene formation, the next step is to do a bromination of alkene. When you will do the bromination of this alkene, you will get a Markovnikov's anti-product, anti-addition product. Now you have vicinal dihalide. So to form an alkyne, you either need a geminal dihalide, chlorine, chlorine, hydrogen, hydrogen with something at it. We don't have to worry about that, but this is a problem. This is what you need. Geminal dihalide or a vicinal dihalide. That is what you need for the formation of your alkyne. So you are going to use a very strong base. So you can get double E2 mechanism. You need double E2 mechanism. This is also E2 mechanism, but only one. So you get only one pi bond. To get a double elimination, you definitely need a stronger base than sodium methoxide or sodium ethoxide or sodium hydroxide. Those are strong bases, but not as strong as sodium amide. And so your alkyne has been formed. You will use, so this is a terminal alkyne. You will do an acid-base reaction here. And once your acid-base reaction is done, you will get your C with the Na negative. Any questions up to this part? Once you have your alkyne, your alkanide, you will need a primary substrate. Now, where do I'm getting these reagents from? I have to introduce them from my own side. They are not given to me. I am introducing them within the synthesis from my own side. But I'm making sure that they are reasonable reagents. I am making up my reagents, but I'm making sure that they are reasonable in makeup. So 1, 2, 3, 4, 5. And my final product also needs 1, 2, 3, 4, 5. And that's how I will get. Now this is not the end. You must know what are the further reactions I can do with my alkyne. I can use sodium ammonia to make what? I can make a trans kind of a structure here. If I had the Lindlar's catalyst, I can make a cis alkene here. So if I have to create a cis alkene from this structure, I will have to follow all of this pathway right here. You can also add HgSO4 and you will get a keto group also. You will not get an aldehyde here because for an aldehyde, you need a terminal carbon. Okay. Now, I know we only have 2 more days before our final exam, but what I wanted all of us to look at is the synthetic strategies. Please make sure that when you come tomorrow, you are familiar, or at least you have a list of all the reagents that we have done so far. So this is the end of all the reactions that you will be seeing. But what I would want all of you to do is to create flashcards, or if you want to make a list, and do it on your own. Don't get from someone else. The thing is, when you will get it, write it on your own, you will organize it in your mind also. Okay. So one of the first things that you can do is if you make a flashcard, let's say you make a flashcard like this, and this is the front, this is the back, let's say. So what you can do is you can write a starting material here. Write a genuine starting material, and then write the reagent that you want to work on. For example, if you want to work on, let's say, bromine in CCl4, let's say you want to do that. At the back of the card, draw the product here, and draw with complete stereochemistry, regiochemistry, and of course, write out the mechanism. So if I have this bromine and I have this alkene, what is the kind of a product that I can get? I'm going to get an anti kind of a product. The mechanism, there is a cyclic intermediate. The stereochemistry is anti, the regiochemistry is Markovnikov's. Similarly, for the same reagent, I have this starting material and I have this product. Right? But what is the reagent that I will need? So at the back, I'm going to write the reagent that I need for this. It can be Br2CCl4, it can be Br2CBr4 also. Then you write the mechanism, the stereochemistry, the regioselectivity. A third flashcard. So this is my first flashcard, but I will make one from starting material and reagent to make the product. I will make from another where I have the starting materials and I have the product, and I don't know what I have to put in the middle. A third kind that would also benefit you is when you have your reagent, let's say Br2, H2O, and like this, BrOH. But now, what is your starting material? That is also something that you will be able to figure out. What is my starting material? So if you look at this structure, that is exactly the same. This OH and Br came on in later. So probably the double bond is between these two carbons. And this is my bond. And I will also write my mechanism, that I have a cyclic intermediate. What is my stereochemistry? What is my regioselectivity? So, this is the time that when the more you will write, the more you will remember. So create your own list. And by writing and revising them again and again, it will definitely help you memorize these. Okay? So make sure that you at least have a list by tomorrow. Otherwise, doing synthesis reactions for our last class tomorrow, we will not be able to benefit a lot from it.
I have a question.
Go ahead. For example, if you have a structure like this. Oh no. So let's say you have a structure like this and you want a product like this, or you have a structure like this, same structure, but now you have a product like this. Same structure, but different products. What is the reagent that you are going to use here? What is the reagent that you are going to use here? So this is where your SN2 and SN1 information will help you. Looking at your products and starting materials. What is the number of carbons? Exactly the same. What is the functional group transformation? There was a OH here, but now you have a cyanide. So that is the functional group identification that you have done. You definitely need a cyanide here, but with what? Do you need it with a H or do you need it with a metal? If you look in your product, is there any rearrangement? There is no rearrangement. The same carbon is what is included. What about the stereochemistry? Your stereochemistry has been inverted. So that is your clue that you have a SN2, because SN2 is the one where you will get inversions. So your regiochemistry just includes with the positioning, especially it helps you with the alkenes positioning. So there is no rearrangement. You can stick with your SN2 habit. So now come back here. Looking at your substrate, what is the substrate that you have? So substrate is a secondary substrate. The carbon with which the polar group is attached is a secondary carbon. You have a secondary alcohol, but you don't have to worry about that right now. Also look at your nucleophile. You will need a strong nucleophile. So with a cyanide, I will definitely put up a sodium ion. I will also need to look at my leaving group. Looking at the leaving group, is it a good leaving group? No, it is not. I need to make it a good leaving group. I need to make it a good leaving group that nothing happens on this carbon, only something happens on this carbon, on this oxygen. So what is my leaving group technique that I will use? The first reagent I will use is MsCl. What will happen here? OMS will form. The second reagent that I'm going to use here is NaCN. So that an SN2 mechanism occurs and an attack of inversion from the back attack occurs. And this is the product that I will get. Also, I have to pay attention to the solvent and other reaction conditions like temperature. If no other temperature conditions are given, I will assume it is room temperature, right? Let's look at the other reaction. I still have the secondary substrate, same bad leaving group, right? But what do I have? Number of carbons, same. What is the function transformation that I see? Which is now SH3. So I need to introduce SH3 somehow. Do I need to put a metal ion here or a hydrogen ion here? So let's look at the rest of the materials also. In my product, do I see a rearrangement? And yes, I see a rearrangement. And that is my clue that I need to use an carbocation. A carbocation formation here. Because in my product, no alkene was formed, I know a substitution happened. What substitution happens with a carbocation? The SN1 substitution happens with carbocation. And so I know I need to use a weak nucleophile here. So I'm going to use my HSH3. What about the solvent and the temperature conditions? I still have a bad leaving group, which I need to make as a good leaving group. So first I'm going to introduce acidic conditions. Acidic conditions will do the acid-base reaction, making this OH a good leaving group. Right? A good leaving group leaves, carbocation forms. What is it that carbocation is going to do? The carbocation is going to rearrange, and I will get my carbocation at the tertiary site. And now my second reagent I'm going to finalize is SH3. And so on my first part of the flashcard, I will have just the starting material and the product. Starting material and the product. And at the back, I can write my reagents with the mechanisms and the conditions that will follow the formation of that particular structure. Okay. Oops. All right, I'm gonna go ahead and close our class for today, and I will see you all tomorrow. Okay? Take care.